Now, as I said, the key here is to get an idea of where we use series in physics. And there's really two places. First is in approximations. And that was in our pre-quiz. I'm not going to really do an example here. We'll be using them later in the class. We might do some on Thursday with it on the problems that we do. But a lot of times, I mean, you're all familiar with this. Classic problem is the pendulum. The forces and torques in the pendulums, you get sines of theta, which, you know, are nonlinear. But if I look at a small angle, sine of theta is approximately theta, and suddenly I have a linear problem and it's easier to solve. So approximations are a big place. The other really big place is solving differential equations. And pretty much, because of Mathematica and other things, we don't focus as much anymore in physics on special functions. There's a few that we do that are critical. But basically, every special function, sine and cosine included, which are a little different because they're defined both in terms of triangles and in terms of solutions to differential equations. But really, from a physics point of view, they're a solution to a differential equation that has special properties that really is defined by its power series. And that's a central idea. Like I said, sine and cosine are a little bit different because not only are they defined by their power series, but you can also talk about them in terms of triangles and angles. So you have a little bit of a two-sided intuition for it. But the basic idea is quite powerful. And we can demonstrate it for actually sines and cosines. And the idea is, if you take the second derivative of this differential equation of x with respect to time, and you set it equal to minus omega squared x, and you want to solve this differential equation, and you forgot that it was a solution that had sines and cosines, one of the things you could immediately do is guess a power series and plug it in. Now, why does this have to work? It has to work because, assuming that the solution is a nice function, any nice function we can write in terms of its power series. Now, it may or may not converge. There may be issues about whether I can actually do it about x equals 0. I mean t equals 0 in this case. But most nice functions and most behavior in physics, the power series will converge, and I can probably expand around 0. But if I happen to know 0 is a bad point, then I expand around something else, like with the natural log. So I'm pretty safe doing this. And it can be a lot of work. This case is not so bad. When I plug into the derivative, what am I going to get? When I plug into the second derivative, what does this sum become? Okay, this is not a particularly challenging question. I'm asking for the second derivative of t to the n. Anyone?
So n minus 2 times n minus 1 times t to the n's power n minus 2.
an times n times n minus 1, okay, times t n minus 2. Excellent. And now this is going to equal the sum from n equals 0 to infinity of minus omega squared a sub n t to the n. Well, that's true. We're really not going to start at n equals 0 anymore. But our original sum did, so I'm leaving it there for now. What has to be true? What is the only way this sum on the left can equal this sum on the right?
The terms for the powers match.
The terms for the powers match, right? We know that t squared plus t cannot equal 0 for all values of t. The coefficients have to be 0. This is the idea of what we call linearly independent that will come back in many, many places. It's one of our unifying ideas in the course. So right away already in series we're seeing ideas that come from linear vector spaces. So the coefficients of every power of t have to be 0 when I bring this over to this side, or the thing won't be 0. Say it again. There are particular values of t that it works, but it can't work for all values of t. And we want it 0 for every single value of t. So just because it's 0 for one point doesn't get us 0 everywhere. Right? That's the key. We need it 0 everywhere. And it's because t is taking on all values that this happens. So this is where I kind of reshift my indices on each side. That's another common trick in physics, is we shift our index. And you're going to have to get better at that. So if I'm making something on the right, t to the n, that was n minus 2, then my a sub n becomes n plus 2. So my n is n plus 2, and my n minus 1 is now n plus 1, t to the n. So that's that becoming that, where I let n minus 2 go to n. And I'm doing this on purpose, skipping a step, right? I could be changing the letter if I was being really careful. If I wasn't good at this, I could have let n minus 2 go to I on the left. And then the math might have been a little clearer because I'm not using the same letter for both. But what I want to show you is the way physicists will commonly do it, so when you see it in your more advanced classes, you're not surprised. We've done this so much that we do it that way. And that gives us the t to the n here, and then these n's are now related to this t to the n. So you want to notice that shift. So I've really made n be n plus 2. Yeah.
What's the relationship between this one, I mean the power series one, and the linearly independent?
The linearly independent is telling me that each power of t separately, when I bring that over to the left or when I equate them, have to be equal, or the coefficients have to cancel to 0. And that's what we mean by linearly independent, is that the only way I can add this to 0 is to make the coefficients, is to multiply by 0 separately.
So why this matter for the...
Well, because up here, I can't get these two sides equal to each other unless every single coefficient for each power of t to the n is equal. So I have to get these powers to be the same number so I can compare the coefficients. And now the other side is already n, so I can just equate.
You want the t to the n?
Oh, sorry, I want the t to the n. Yeah, thank you. Because now I'll cancel my t to the n's. Having done that, I get what's called the recursion relation. A sub n plus 2 equals minus omega squared over n plus 2 times n plus 1 a to the n. Now, even though in Mathematica I could just go in and do desolve, and I'll show you that in a moment, and get the solution of this differential equation and do a lot of stuff, by looking at our power series solutions to a physics problem, we often learn some interesting physics about the system, even if we don't know anything about the function yet. So what is the interesting physics I've isolated here by doing a power series, by using the power series? What is a key thing in this recursion relation? So just take a minute, talk to the people next to you. Is there anything cool about this that you immediately recognize? There's probably 2 facts that I would be looking for you to notice. So go ahead, chat with the people around you. What 2 things do you notice by looking at this recursion relation? Well, chat with, find someone to chat with. Or think in your head if you're not feeling friendly today or you're not near anyone, you can just think about it yourself. So it kind of got quiet, so I'm going to assume we have brilliant ideas already. What have we noticed about this? Well, no, we know nothing yet about sines and cosines just from looking at this.
The denominator is going to be some n plus 2 factorial.
The denominators will ultimately be factorials as we keep going, because we're always adding the right terms to get that. But that's not the physicsy thing I was looking for, but it's a good thing to notice.
I think boundaries because of the denominator. I'm not sure.
Possibly. Okay, this is interesting. Notice, see, this is why we redo this class, because mathematicians don't care about these things as much. Do you get every term in the power series? No, you're only going to get what? What powers of t are you going to get? Every one or every other? So if I start with 0, do I get any odd powers of n? No, because I get 2, 4, 6, 8. If I start with 1, do I get any even powers of n? No. So this function is either what? Either odd or even. I've just discovered that I have 2 solutions depending on what I start with, and they're either odd solutions or even solutions. So there's a symmetry here that I've discovered in my solutions that are going to be based on my initial condition. How many free constants of integration should I have to this differential equation? I started with what type of differential equation? How many derivatives? 2. So how many times do I integrate to solve it? 2. So how many constants of integrations do I have? 2. So how many unknown constants do I have in my power series here? 2, right? A0 and A1, I mean, I can pick others, but basically A0 and A1 are free parameters, and if I start with A0, I get an even series. If I start with A1, I get an odd series. That's a key physics sort of insight that I get from my recursion relation. Less key, this is more along the lines of the factorial, which I liked, and some of the other things. Is it an alternating series, or is it always the same sign? It's going to be alternating, because every time I multiply this minus by the previous factor, I'll switch between positive and negative. So I also notice it's an alternating series. That's probably a little less interesting from a physics point of view, but it's a useful thing to notice. Now, what I want to do, I want to show you and give you a flavor for how this would be a little bit different in Mathematica. The problem is, at this point in the course, the Mathematica you need to do this is more advanced. If I just jumped into it, it would be incredibly confusing. So I'm going to show you a few pieces to it. And then what I'm going to do is, and I'll do this periodically with the class, I'm going to prepare a separate little video of me just doing the Mathematica, and I'll post both the Mathematica file and the video. So as the course goes on and as you become more comfortable with Mathematica, you can go back and see what's happening. But let's just look at some of the features that would be involved. And the first key idea in this is, in Mathematica, we use equal signs in lots of different ways. So I can set x equal to t plus 6t squared. And that's assigned the expression t plus 6t squared to x. X is now equal to that. I can also use a double equal sign. And that's going to be a comparison thing. Is 2 equal to 3? It's not, so that's false. Or I might do, is 2 equal to 4 divided by 2? And that's true. So if you want to compare two things, you would use the double equals. If you want to just assign something a value, you use the equals. Now, the danger is, and this happens, you might have, so f equal to x plus 4x cubed. And you want to look at this for a particular value of x. Notice, Mathematica remembers that I had set x equal to t plus 6t squared. So f is now known in terms of t. If I had done it a different way, so let's clear the value of x. Oh, it still remembers that, so let's clear f. And now let f equal to x plus 4x cubed. We're back to that. Now, maybe I want x to be 6. If I let x equal to 6, now f is in terms of what 6 is. And it no longer remembers the functional form of f. So if I clear x, let's see. In this case, I'm back because of the order in which I did it. I never let I let x equal 6 afterwards, so I only had to clear x. So f is now remembered. A better way to do this, and this is unique to Mathematica pretty much, and is critical for you to learn, is replacement rules. So now if I do f slash dot x goes to 6. Notice what it's done. I've got the same answers when I let x equals to 6. I got 870. But now if I type f is unchanged. The slash dot says I'm about to make a rule. The rule is wherever I see x, replace it with 6 for this expression only. And so it's going to plug in 6 for x. And it'll work, and it'll give you the right value. And this is used in many, many places. The main reason it's used is, let's suppose I have the equation x squared minus 4 equals 0, and I'm going to solve it for x. That equation has two solutions. Mathematica doesn't want to return x equals to x equals minus 2, because the last equals it does is what x will be. And then you're stuck with x being that value. Mathematica wants to give you a structure that allows you to use those solutions in whichever solution you want later on. So solve, desolve, any of Mathematica's things that are solving stuff is going to give you a rule. And the fact that it gives you a rule means you need to know how to use rules. So now I could take these, and let's actually make life a little bit easier. We'll give it a name so I can use it. And now if I look at Mathematica's structure of looking at vectors, it uses a double bracket to index a vector or a matrix. And we'll do more of that later on. So I'm going to pull out the first element, which is just the rule x goes to minus 2. So I can do f slash dot solution of 1. So what did I just do? I'm telling me to use a rule. The rule I'm going to use is this rule here that was my first solution. And then I want to know what f is when x is minus 2. And that's how you piece together solutions and substitute into things. And it's a fundamental piece of Mathematica. So for many things, instead of using a function in Mathematica, you would use an expression like this and then evaluate it using rules. That's a common thing to do. Now, I keep clicking on the wrong slide bar. I still have one other equal sign I can use. I can make a function and the notation in Mathematica to make a function is g of x with an underscore. That's telling me this is my dummy variable. So this won't let x be anything. I can use x later as a variable. And colon equals is telling me to assign this as a function. So this is the other piece of sort of syntax you need to know. And now I can use g of x just like I would any other function. I can write, g of 2, and it will evaluate. The most common question I get in Mathematica is when do I use these and when do I use these? When you want to. Most of the time in many applications, if you know you're going to be doing a lot of substitutions, you'll find both of these seem to work. The one time you really want to be comfortable with rules is if you're going to be solving either differential equations or algebraic equations. Mathematica is going to give you rules as your answer, so you want to be prepared to use them. So I find my tendency is to most often use rules and not bother with functions in Mathematica. If I'm building something complicated, I will occasionally use functions. And you'll see, we'll do a little bit on how to make short little programs. If your function is a mini program, you're going to use this function notation, right? If your function has multiple steps, if it's not just some algebraic expression, you're going to use this notation, right? Because you might have a function with an if statement in it, or a do loop, or anything like any sort of normal programming subroutine you would use the function notation for. Anytime you're going to be expecting to use solutions to an equation that has a rule, you'll probably just use an expression that you then use the rule for. The reason I put this here is if we now were to do our example that I just did, I would make a differential equation, say y double prime of t, plus, I'll keep omega 0, y of t equals 0. Now, I can solve this. Now, in solving differential equations, you need to tell it the differential equation you're solving, the function you want to solve for, which is y of t, and the variable that's everything is with respect to t. And notice I get cosine plus sine, I get my two constants, and I get it as a rule. If I want to do the whole thing we just did with power series, the key step that's different is I'm not going to use an infinite power series and solve for the recursion relation directly. Most of the times, I will pick a finite power series that I define and I use a notation here. The single brackets are often a function. The one other quirk in Mathematica is I can use them basically as a subscript to get coefficients if I'm doing some indexing over a variable. So I will make my sum. I will use my substitution rule to plug into the differential equations. I will collect terms. I'll set them equal to 0. And then I'll solve for my recursion relations. The trick is, if I'm doing a substitution into here, I need to also tell Mathematica it's a function. So there's a lot that goes on there that I didn't have time really in class today to go through. I wanted to set up for you the basic process. And like I said, I'll prepare this as a separate mini lecture for you to look at as we build up more Mathematica and to come back to. The process is basically the same. It's make a power series, substitute it in, collect terms. In this simple case, Mathematica versus doing it by hand, probably about the same. Right? That was a pretty easy recursion relation for us to solve for. Mathematica, once you know the commands, it's pretty easy to do. But imagine you have a new differential equation with a lot of terms that's very complicated, and you want to do a power series solution. Mathematica allows you to do it without actually having to do any algebra. It's the same set of commands. In fact, you can write a program to do it. It's that rule-oriented, and in the Mathematica handbook, there is a program for it that you could copy. So any differential equation, you can get the power series solution for by just following the logical steps and rules without actually having to do any algebra. And that's kind of the cool thing about Mathematica. The more complicated the problem, it's just as easy as an easy problem. Any questions on that? There was a lot there, and this is most of the time, and once you get through the first two tutorials, all of this will be easier. A lot of the Mathematica in class, please stop me if you have questions, but a lot of it, until you use it yourself, it doesn't make sense, and that's why we'll be doing some Mathematica problems on a lot of the Thursday problem-solving sessions. Because the easiest way to learn the Mathematica is to do it in front of me, not to watch me do it. Okay. The last final note on series, and again, I'll show you this later in a Mathematica file, is we do have to be careful that sometimes series converge but are not real useful, and sometimes they diverge but are useful. And as a Mathematica practice, I'm going to have you kind of try and do this exercise because it's a little practice in plotting. So once you get through the tutorial later on, we'll come back to this. But I said Bessel functions are one of the special functions that we know about. And the cool thing about them is you can write them as a power series. It's kind of a weird power series. Because it's got 2 factorials in the denominator. This power series converges, but is very inaccurate as r goes to infinity. You need way too many terms to actually get a good approximation. There's what we call an asymptotic series for I naught of r. Because for very large r, it behaves basically as e to the r over r. So we can take that term out, because that's its infinite behavior, and add a few terms of powers of 1 over r. This series does not formally converge, but at very large r, it's actually quite accurate. And it's quite accurate because you've correctly pulled out the asymptotic behavior. And that's something we use a lot in physics, or is what we would call an asymptotic series, one that works well in a particular regime, even if the series itself doesn't converge. So that kind of concludes our 3 main ideas of series. I didn't really do the approximating of functions much. That's something you've done a lot before. We went through a few quick ones. The solving differential equations is one of the most powerful and useful places of series, and it comes back a lot. And then just this idea of getting a good approximation even if the series doesn't converge. Any questions?
Would you please give a quick review for the converge and diverge for series?
Say it again.
A quick review for the definition of converge.
Well, a convergent series is one that the error just keeps getting smaller and smaller, and as you take the number of terms to infinity, it actually equals your function. It doesn't diverge or become infinity, right? For instance, if I add 1 plus 2 plus 3 plus 4 plus 5, and I keep adding up to infinity, that series diverges. It becomes infinite. So this series, if you do it, diverges. It doesn't converge to a finite value. But if you only take a few terms, it's actually a very accurate representation at large values of r.
Is the curly bracket saying that?
Oh, no, the curly brackets just, I didn't match my brackets. I just felt the mode.
I was just wondering if it was e to the r over square root of 2 pi r divided by the entire.
Yeah.